have to see the catchment, the river, the physical being. So, let's think at the river flow series, river flow data. And the first thing that I want you to focus on is that the data are positive. Because of course they cannot be negative. Unless you make some transformation, like subtracting the mean, the data are positive. And positive means that they are greater than 0. And usually, there are a lot of data which are close to, let's say, 0, and a few data, the flats, which are very high. So you have what is called a long tail of the distribution. So if you write the probability distribution, fx, the density and mean, usually you find something like this, and a long tail. For instance, let me give you an example of a river that I know quite well, which is the Setia River basin. The Setia River is a river that is located between Modena and Reggio Emilia, and has a catchment area which is about 1,000 square kilometers. It's similar to the Reno River. Its catchment is more or less the same size. And for this river, the average river flow is about 20 cubic meters per second. So we have a lot of data that are concentrated around this value. And the river flow with a return period of 100 years is about, at the closure section of the mountain basin, is about 1,000 cubic meters per second. So you have the average, which is about 20, and then if you get to a return period of 100 years, you are about 1,000. If you think of the Po River, if you look at the daily data, you see that the Po River at the closure section of Ponte Lagoscuro, the average is 1,500 cubic meters per second, and the peak flow with a return period of 100 years is about 13,000. So it's a similar distribution. And this is, of course, physically very meaningful because you have a lot of days in which you see a river flow that is close to the mean. And therefore, you have a peak in the probability distribution because the frequency of the observation is very high. And then you have a few days in which you have the floods, typically 3-4 floods in relevant floods in 100 years. And therefore, you get this long-tail probability distribution. But what happens if you take the logarithm of this data? If you take the logarithm, the reduction, you obtain a reduction of the data. The data becomes smaller, but the big flows are much more reduced than the low flows. You know this. So when you take a logarithm, if the variable is small, you reduce it, but not as much as you reduce a big value. So basically, what you obtain is that the tail becomes much shorter. So you become closer to Gaussian because the distribution that you obtain is like this. You get something like this. Maybe it's still not really symmetric, but indeed you get closer to Gaussian. So the logarithmic transform, the log transform, is something that really may help you a lot. And it has a great advantage that it's non-parametric. Non-parametric means that you don't need to estimate any parameter in this transformation. You just take the logarithm. And I just want to draw your attention on the fact that the logarithm is defined only for positive data, which is not a problem for us, because when we deal with river flow, rainfalls, and other hydrologic data, often they are just positive. But for instance, if you deal with temperature, then you have to be careful before taking the logarithm. It may be not a suitable transformation. And also, this note that I'm presenting to you now on the positivity of the data means that if you want to take the logarithm, it should be the first transformation that you make on the data. Because if you apply decisionalization first, you get negative data. A decisionalized series may end up with negative values. So if you think that it's the case to take the logarithm, this is the first transformation that you have to make. Because you know, you may have the need to perform many transformations, like transformation to make the data Gaussian, and then a transformation to remove seasonality. And this means that then Gaussianity should come first and seasonality second. It doesn't change much when you have to perform many transformations, the order. But in some cases, the order is important, like in this case, for technical reasons. And what is really important, pay attention, is that when you apply the anti-transformation, you respect the same order. It is an obvious consideration, not the same order, the reverse order. It is an obvious consideration, but please don't forget it. There is another transformation that there are more other transformations that can be used to make the data Gaussian. This is just the simplest one. Sometimes it works, sometimes not. So this is the reason why in hydrology people devised other transformations. Some of them are parametric. I just want to mention to you one. I need just the name because I don't want to insist much on this topic. And it's the Box-Cox transformation, widely used, parametric. There is another transformation that I want to explain to you. It's a bit complicated, but it's gaining a lot of popularity today, so I think it's interesting that we spend some time on it. And this transformation is very powerful with one limitation. Which I'll tell you later. So let's start with the data, xt. And let's write them in ascending order. Let me think if it is ascending, increasing or decreasing. It's better if I use increasing or decreasing. And let me think. I think it is, okay, it's increasing, yes. And this data, the number of data is n. Total number of data is n. Now, let me compute here, and the number of data is n, and let me write here a column, which is called I, which is the rank. And the rank is varying from 1 to n. So the lowest number is number 1, the highest number is number n. Good. Now let me compute in another column here this quantity, I divided by n plus 1. And you would obtain a number which start from 0.00 something and gets to 0.9999 something. The number of nines is not determined, like the number of zeros. It depends. But the concept is you start from a number that is close to 0 and you end up with a number that is close to 1. So what is this number? Is represent the frequency of not exceedance of each observation. Frequency of not exceedance. And let's try to better understand. If I look at the lowest number, it is exceeded by all the others, so has a very low frequency of not exceedance. I'm talking of the lowest. The lowest number was exceeded by all the others. So it has a very low frequency of not exceedance. In fact, it's 0, 0, 0 something, close to 0. The highest number was never exceeded. So it has a high frequency of not exceedance, close to 1. And you may say, why you divided by n plus 1 instead of dividing by n? This is just a statistical trick to make the estimator more reliable. If I divided by n, I would obtain a frequency of not exceedance of 1 for the highest number, which is not what I would like to get, and I'll explain you in one moment why. Now, let me assume that this frequency of not exceedance is a good estimate of the probability of not exceedance of each observation. And I can do that because I know by definition that the frequentist definition of probability is indeed satisfied if we assume that the probability is given by the frequency of the event. So it's fine to match the frequency of not exceedance with the probability of not exceedance. But then you can understand why I don't want a probability of not exceedance of 1 for an observed number. It would mean that I am assuming that that number cannot be exceeded, which is, of course, it's a wrong assumption, because if you look at the time series of a river, even if it's 10,000 years long, you may always have in the future an event which is greater. So it wouldn't be physically meaningful to give a probability of not exceedance to the highest number. So this is the reason why you put a plus 1 here. Now, let's call this as fx. Let's call it f, capital F, x, frequency of not exceedance. And now, let me put here another column where I get a second variable, let's call it z, which is given by inverse normal of zt. What is inverse normal? You have a probability, which is given by this column. You compute the quantile of the normal distribution of such probability. Inverse normal because you go into the distribution with a probability and you take from the distribution an observation. This z is normal for sure, because it's an outcome from the normal distribution. So it's for sure normal. So you see that this transformation, and inverse normal, you can use normal 0, 1, because you can use whatever parameters you want to use. Usually people use the normal 0, 1, and just because it's easy to handle. But in any case, you get outcomes from a normal distribution. And you see that this transformation is very easy, it's not parametric. So it's really easy to do. And so one may say, oh, so why shouldn't I use this transformation always? Yeah, there is a problem here. And the problem is this. Let's suppose that you have a graph where you represent xt and the corresponding zt. And usually this graph is done in this way. It's something like this. The tail is reduced, you see. Here on x you have a long tail, like this long tail, and if you look at the projection of this long tail on z, it's much shorter. So this is a graph that you get, which is so far so good. But if someone asks you, what is the x value that corresponds to this z, which is not covered by the observed data, who knows? So the transformation just covers the range of the observed data, but if you perform a simulation and you aim to get data that are outside from the range of the observed, which is usually like so. When you perform a simulation, in our case, is because you have only a few observed data. So for sure you want to get observations that are out of the range of the observed one. So you don't know really how to anti-transform them. So the problem is anti-transformation. By the way, this transformation is called the normal quantile transform. And is often indicated with the acronym NQD. One last thing that I wanted to tell you is we have tests to check for Gaussianity. I'm not going into the details. You will see on the slide that there is a slide dedicated to one test for Gaussianity, because at the beginning you may be in doubt whether or not your data are Gaussian, and there are tests. I'm not giving any detail to you. Okay, so let me now some final considerations on this type of stochastic process that we considered, which is autoregressive process. And then in the next hour I will explain to you very briefly, without details, a second type of stochastic process, and then we are finished on this, and then we move to water resources management in detail. And let me give you a couple of details on this process. And first of all, it's very simple, as you have seen. And there is a huge literature on this project, on these processes, type of processes, and they are usually indicated as autoregressive processes, but there are many variants of this model, which translate in extensions of this algorithm, of this acronym, sorry. And the most known variant is the class of the autoregressive moving average processes. So you have to add moving average. And the acronym is ARMA. And usually, autoregressive processes are considered a special case of ARMA processes. So I'm just giving this information to you because this class of processes is very well known. And there are other extensions. ARIMA, which ARIMA means integrated. Integrated, the process becomes non stationary. Integrated means that when you generate an autoregressive process, if you take the cumulative sum, the integral of the data that you generate, you get a non stationary process. And it's called ARIMA, and many others. We are not going into details. And another issue that I wanted to mention to you, these are linear models. We know that. What does it mean linear? It means that if you have an intermittent series, you cannot reproduce this intermittent series with these processes. Because you can get a series of zeros with a linear model. If you get a model like xt equals phi 1 x t minus 1 plus epsilon t, how can you get a zero? It's impossible because this epsilon t, if it is a random variable and it's Gaussian, can take value 0, but then the next one will be different from 0. It's impossible to get a series of zeros here. And also, if you focus just on the deterministic part, you understand that you cannot get an intermittent process from here. Because if you start from a given value xt minus 1, you get something that is different from 0. It may converge in the long term to 0, but then, if you want to get back to a value that is different from 0, you can't get back to this linear relationship. So it's not possible. And therefore, if you want to represent rainfall, this model is not fine. Rainfall is typically an intermittent process. Or if you want to represent flow regime for a torrent, which is an ephemeral stream, meaning that you have some days in which you don't see any river flow, this process is not fine. You have to use other stochastic processes which are not linear. And we will see an example without going into the details in the next hour of a more linear stochastic process. It will be a very short example. Okay, now let me make 15 minutes break and I try to show this fascinating problem. Very easy. Use your expectation.